Lovely. Well, all of that out of the way, we've got a couple of minutes left to just start on our applications of induction. So the concept of induction is very, very important and has a whole bunch of applications. The syllabus asks us to look at two specific applications, which are transformers and electromagnetic braking systems. It also is very important in motors and generators, which I don't think we'll get to, but you've got the slides, so if you're interested, you can look ahead on the slides. So let's firstly take a look at the idea of eddy currents. Eddy currents are circularly induced currents that sit on the surface of flat conductors. Basically, what that means is that when you have a big sheet of metal and you pass a magnet over it or some kind of magnetic field passes over it, Lenz's law, remember, Lenz's law said that if you have a conductor and you have a change in magnetic field, that's going to induce an EMF. The difference here is that because rather than it being like a coil, it's like a massive, big, proper sheet of metal. When you induce a current on it, the current kind of doesn't know where to go, and so as a result, it will move in a circle. And that circle is what we call an eddy current. Um, yeah, so it's theoretically nothing new. It's just Lenz's law being applied to rather than a circle, sorry, rather than like some kind of circuit, it's being applied to like a full big massive sheet of metal instead. Yeah, so that's what an eddy current is. Now, it's going to be used, in this first example of electromagnetic braking systems, it's sort of the goat of electromagnetic braking systems, it's what we want. However, it's kind of annoying because it then means that if you've got a sheet of metal and you have a magnetic field passing through it, sometimes you accidentally get a current flowing through it, which might not be great if you don't want that current to be flowing through your metal, as we will see in transformers. So, an electromagnetic braking system essentially works by having an electromagnet passing over some kind of wheel. So you can kind of imagine that this triangle here, sorry, triangle, you can tell I've been speaking for like 2.5 hours. This rectangle here, sorry, you can kind of imagine is like a side-on view of a nice circular or cylindrical wheel. So imagine that this is not a great drawing, but imagine that this is just like a side view of our wheel. You slap the electromagnet on the sides of the wheel, and that passes some magnetic field through the wheel. And then as the wheel spins, from the perspective of like a little piece of metal on the wheel, it then enters into the magnetic field on one side and exits out the magnetic field on the other side. Which means, remembering back to Lenz's law, we have some kind of change in magnetic field as we're passing through, which means we've got some kind of change of flux as we're passing through, which means we are going to induce some kind of current. And as that current that we're talking about is going to be that eddy current that we're dealing with over here. And yeah, so that's essentially how we're going to induce eddy currents. So to recap, we've got an electromagnet over the top of our metal wheel. As the wheel spins, it goes sort of in and out of the magnetic field, or like different points on the wheel will go in and out of the magnetic field. And so as a result, we will get these little currents induced on the surface of our wheel. And those eddy currents, they sort of serve two purposes. They will first of all just exist, which means they will like dissipate heat. Because they're currents flowing through a wheel, they sort of will like encounter resistances and they will turn into heat. And if you sort of think about the law of conservation of energy, that means we're taking the motion of whatever is moving the wheel and we're converting its kinetic energy into heat energy. We're sort of dissipating its energy as heat, which is going to slow it down over time because we're taking the kinetic energy and we're getting rid of it. We're turning it into heat. The other thing it's going to do is because it's going to act by Lenz's law in such a way to oppose the motion, it's going to sort of induce a magnetic field to just kind of repel itself from like the electromagnet. And so as a result, that's going to sort of slow the wheel down because it doesn't want to spin anymore. It doesn't want to go through the electromagnet. And so that sort of aligns itself in such a way that it tries to sort of slow down. Now, just to do a little bit of practice, I might sort of end on this thing then, just so I can go into it in a bit more detail. We can sort of analyze what's actually going on, and we can apply what we learned in Lenz's law to actually figure out like which direction are our eddy currents actually going to move. So Imagine that you're a little spot on this wheel, and the green dots, by the way, are the magnetic field, like that's acting on our wheel. And you can imagine that you're a little dot on the wheel, and then you're slowly getting pulled in. Well, not slowly, but like if you're moving really quickly, you're getting pulled into towards this magnetic field. Thinking back to our Lenz's law structure, right? The first thing that we want to do is we want to figure out like what is the change in flux? Well, the change in flux is we're going from having no magnetic field to having some magnetic field. Basically, we're gaining a magnetic field. Um, and Lenz's law says we want to oppose whatever change is happening, which means we want to oppose the flux that is like being created, which means we want to cancel it out, which means we want to induce a magnetic field that's acting in the opposite direction. So we could sort of say like our ideal situation is we want to have a magnetic flux that's moving into the page, right? It's going in the opposite direction to the magnetic field that we currently have because we are increasing the flux, so we want to decrease it by like canceling it out. Now, once we figured that out, we've sort of done the hard part, and all we have to do is use our right-hand rule to figure out, well, which direction are the eddy currents going to be moving in. And if you do that, you find out, oh, wow, look at that. Your thumb's pointing into the page. Your fingers are then all going to be pointing in the clockwise direction, which means, wowzers, we have a current that's moving around in the clockwise direction as well, which is very cool. So that tells us over in this direction, we've got a current that's moving in the clockwise direction, and we can do the same thing over here. So sort of like on the other side of the wheel as well. So imagine you're a point that's currently like inside the magnetic field, and then the wheel spins and you get pulled outside of the magnetic field. Well, that's also a change in flux, right? We've gone from having some magnetic field to having no magnetic field, which means in this case, the change in magnetic field is that our magnetic field has disappeared. But Lenz's law once again says we want to oppose that change in flux. We want to stop it from happening, which means we want to cancel that change in flux out. And the change this time was getting rid of magnetic field, which means what we want to do is we want to induce magnetic field, right? We want to create the magnetic field. So we want to make a magnetic field going out of the page, coming back out towards us. So once we figured that out, we want to have the magnetic field coming back out of the page towards us. We can use our right hand grip rule and you can point your thumb back towards yourself, fingers curling around, and we have an eddy current. We want to have eddy current moving around like that. So that basically tells us another way of thinking about that is that we're going to have an eddy current moving around, and I think I've actually got it on my next slide. We're going to have eddy currents moving in a clockwise direction on this side and an anti-clockwise direction on that side, which is going to induce exactly the magnetic field that we said that it was going to induce just beforehand, right? So it's going to be a magnetic field going into the page over here and a magnetic field coming out of the page over here. Let's pause for a second and think about what that actually represents. That means that as we're entering the magnetic field, basically on this side, we've got a magnetic field that's so we're going to slow down. And so that's essentially how our electromagnetic braking is able to operate correctly, which is very, very cool. Okay. Yeah, so this slows down the wheel for two reasons. Firstly, the eddy currents will heat up the wheel, which converts its kinetic energy into thermal energy. And then also the eddy currents generate their own magnetic fields, which are going to oppose the wheel's load motion, which is what we saw over here due to Lenz's law. Okay, I've got like 4 minutes left. Let's speedrun just an elementary idea of what a transformer is. So a transformer is a device that either increases or decreases the voltage of an alternating current. Basically, you can have an AC voltage and a transformer is something that will change it. It either steps it up or it steps it down, where a step-up transformer basically increases the voltage and a step-down transformer decreases the voltage. And yeah, so it's incredibly useful. It's a very, very important device because it's something that basically is the backbone of most of our modern power grid, because the voltage that is generated at the power source is probably not going to be particularly useful if you try and plug your laptop into a 1000 volt supply that's being generated off in a wind farm somewhere. It will probably explode your laptop. So instead, you've got to use a transformer that is going to step down the voltage. In fact, you potentially even have transformers inside your like charging cables themselves to like step up or step down voltages to give it just like to change the voltage from whatever the thing is that's coming in to perfectly whatever voltage you need that's coming out. So yeah, that's essentially why step up and step down transformers are important, is because like not every single electrical device needs exactly the same voltage. So instead we have to sort of wiggle them around a little bit. Now, one quick question I've got for you is just to think about is why do you have to increase a current to decrease the voltage and vice versa? Because a step down transformer is going to increase voltage and decrease current. A step down transformer is going to decrease voltage and increase current. If you want to pause the video and think about this just for a second, you can. But the answer is essentially because of the law of conservation of energy once again, right? We can't run away from that sucker. But it basically tells us that the power that we supply into a transformer has to be the same or more than the power that comes out of the transformer. Basically, we can't generate power inside our system. And if you remember, power is equal to current times voltage or voltage times current, which means that the voltage and current that we input, we could call it like the initial current, needs to be equal to the voltage and the current that we output, the final current and the final voltage. Which means if we increase voltage over the course of our transform, like our voltage number increases, because we need like the net change to not be there, in order to compensate for that, we would need to decrease our current as a result, and vice versa. Now, speedrun, 1 minute, how it essentially works is if you provide some sort of alternating AC current passing through the first coil, it generates a changing magnetic flux, which then passes through the second coil. And that changing magnetic flux, by Lenz's law, what we've been learning all about today, with our induction topic, that will generate a current in the second coil, which we can then, that will induce an EMF, which is a voltage in the second coil, and that's how we can transfer it across. And basically then we have these formulas that tell us what the relationship between all of our different things are, which is absolutely lovely, and allow us to manipulate the voltages inside of things. Anyway, I'm basically out of time. I'm very sorry that I didn't get through the rest of this. Transformers, there's sort of two things you can do with them just from an HSPC perspective. You're going to need to know what your formulas are, and you're also going to need to know how to design transformers to make them really good, because the eddy currents that we were just talking about with electromagnetic braking, even though they were so important for electromagnetic braking, they are kind of very annoying for transformers because they mean that you lose power, which is not wonderful. So we have to do a bunch of stuff to fix them. And then the final topic for this module is motors and generators, which is kind of where we get into the dirty of like how do we actually use electricity to do some interesting stuff and do all of the things that we have seen so far. But anyway, I am out of time for today. If you want to, I would really encourage you to download the slides and go through the rest of it by yourself if you want to. But otherwise, thank you for sticking around for the whole video. I'm so sorry once again.